AI image generators don't search the internet for pictures. They don't have a database of images they copy and paste together. What they actually do is far weirder and more interesting than that. They start with pure noise, literally random static like a broken TV signal, and they progressively sculpt it into a coherent image guided by nothing but a text description. Understanding how that works will change how you think about these tools entirely. The dominant technique behind tools like Midjourney, DALL-E, and Stable Diffusion is called diffusion. The name comes from the direction these models learn to work. During training, the process goes forward, take a real image, add a tiny bit of random noise to it, add more noise, until after hundreds of steps the image has been completely destroyed and all you have left is random static. Do that to millions of images. The model watches this destruction process over and over, and it learns to reverse it. When you actually use the model to generate an image, you run that process in reverse. You start with random noise. The model predicts what tiny amount of that noise should be removed to make the image slightly more coherent. Remove that noise. Predict again. Remove again. After hundreds of steps, the static has been transformed into a crisp, detailed image. This is called the denoising process, and it's what's happening under the hood every time you hit generate. But here's the key question. How does the model know what kind of image to sculpt toward? How does it know you want a sunset over mountains, not a portrait of a dog? That's where the text comes in. The text prompt you type is converted into a numerical representation, a kind of mathematical fingerprint of your description, using a separate model trained to understand language. That fingerprint is fed into the diffusion model at every denoising step, guiding the process. It's like having a compass that constantly nudges the sculpture in the direction of your description. This is also why prompt engineering matters so much for image generation. Slightly different wording produces dramatically different results, because the language model that converts your words to numbers is sensitive to phrasing, specificity, and style references. Saying a photorealistic portrait of a woman in soft morning light produces a very different result from saying a woman in light, because every word shifts the mathematical fingerprint. The model also learned visual style during training. When it saw millions of images, it absorbed not just what objects look like, but what oil paintings look like, what photographs look like, what anime looks like, what a Rembrandt looks like versus a Monet. When you include style references in your prompt, you're activating those learned associations. Now let's talk about what the model has actually stored. It's not storing images. There's no gallery of pictures inside it. What it has stored is billions of learned weights, the parameters we talked about, that encode statistical relationships between visual features. Essentially, it knows that certain pixel patterns tend to appear together. Eyes with noses and mouths, wheels with cars, clouds with sky. When denoising, it uses those learned relationships to produce images that look statistically like real photographs or artwork. This is also why AI images sometimes have strange errors. The distorted hands, the extra teeth, the background that doesn't quite make sense on close inspection. These are places where the model's statistical understanding breaks down, where the patterns in the training data weren't consistent enough to give the model a reliable model of how these things should look. Hands are hard because human hands appear in photographs from every angle, partially hidden at every scale. The patterns are noisy. The model's learned representation is shakier there. One other component worth understanding is the latent space. Instead of working directly with pixels, which would be computationally brutal, most modern models compress images into a much smaller mathematical representation called a latent code. The diffusion process happens in this compressed latent space, and only at the end is the result decoded back into actual pixels. This is why the models can run at all on consumer hardware, and it's why you sometimes see that characteristic slightly smoothed or painterly quality in generated images. Training these models required billions of images scraped from the internet, along with their captions and associated text. This has raised real and ongoing legal and ethical debates about whether using copyrighted images without permission for training is acceptable. It's a genuine conversation happening in courts and policy circles, and it's worth following. What these tools are genuinely extraordinary at is rapid visual ideation, concept visualization, and style exploration. A graphic designer can generate dozens of rough concept images in minutes. A game developer can prototype art direction before commissioning final assets. Anyone can visualize an idea without knowing how to draw. That's a real and significant capability shift. If this helped you understand AI art generators, subscribe. We break down AI every week in plain English.